Before we start learning about our new assembly instructions, just a quick reminder about multiplication in general on computers, given that we have limited and fixed register sizes. In general, if you multiply two registers together, very often the results will not fit into the same size register. And generically speaking, if you multiply two x-bit registers together, you will need at most 2 to the x bits worth of space to store all the possible values. Giving you a concrete example, let's pretend we had 1-byte registers. The values are 0 to FF, but even the small values of hex 10 times hex 10 yields hex 100, which does not fit in a 1-byte register. And the maximum values of all Fs times all Fs yields FE01, which again does not fit in a 1-byte register. You would either need to have a 2-byte register available, or you would have to store the upper half into a 1-byte register and the lower half. Same thing with 4 bytes and 8 bytes and everything else. I'm just using 4 bytes here because it's a little smaller. 10,000 times 10,000 yields 1 and 8 zeros, but those 8 zeros are like the least significant 4 bytes, and the 1 is now overflowed into an upper 4 bytes that would be necessary to store this result. And so the same thing, all Fs times all Fs would give us E 000E, which obviously doesn't fit in a 4-byte register. You would need either one 8-byte register, or you would have to store the upper 4 bytes and the lower 4 bytes. So the same principle applies to computers no matter what size of registers you're using. Here in our code, it is 64-bit, and therefore we have 8-byte registers. But the same thing if you had RV128 and they had 16-byte registers, you always have this potential that if you're trying to multiply native register size like xlang times xlang, you're going to need 2 times xlang worth of space. So also one property about binary multiplication that I want to inform you about, and here I've borrowed a slide from this ARM assembly for embedded applications textbook website. And there is a mathematical property that whenever you're doing some xlang, here we'll say is 4 bits, some xlang times xlang thing, the result will be 2 times xlang, but the bottom xlang will always be the same regardless of whether the input parameters are interpreted as unsigned or whether they're interpreted as signed. So you can go ahead and go see that book and the website and go to the integer arithmetic, which is where this slide is from, and he'll show you the mathematical reason why that's true. But I'm just going to hand wave and say, just assume that if you multiply two xlang registers together, the bottom bits will always be the same for the multiplication, regardless of whether you interpret the values in the registers as signed or unsigned. So RISC architectures like RISC-V or ARM will take advantage of this property, and they will have multiply instructions that will give you only the lower half, and then separate multiply instructions that will give you the upper half, depending on whether it's interpreted as unsigned multiplication or signed multiplication. And we're going to see the same pattern play out here in RISC-V. So example 1, MulDivRem. So we have our uint64 defined as unsigned long long. So we have an A, which is unsigned long long, and we initialize it to defected. We multiply times detectable. We divide by too bad so sad, and we modulus by lol, or 101. If we compile this at optimization level 0, we get the following assembly code with 3 new assembly instructions, mul, divu, and remu, seemingly associated with our multiplication, division, and remainder or modulus operation. So first, mul. Mul is a multiply that keeps only the lower xlang bits. And this is because, as I said before, when you have xlang times xlang multiplication, the lower xlang bits will always be the same regardless of whether you have signed or unsigned operands. So just rs1, the source 1, times rs2, the source 2, keep only the lower xlang of the product, and store it into destination. And that's exactly what that's saying. Looking at a concrete example of that, let's say we had multiply T2 as our destination, T0 and T1 is our source, T0 set to 2 times T1 set to 8, and so 8 times 2 is 16, and that is hex 16. That's expected. Now, a little more complicated, we have T0 of 2, T1 of all 8s, and if we multiply these together, we see that the result is somehow smaller than the inputs. Well, it's not smaller, it's just that this overflowed the 64-bit available space, and this is now only keeping the lower xlang bits, the lower 64 bits of the product. If we wanted to see the upper xlang bits, we will have to use a different multiply instruction to keep the upper or high bits, which we'll learn about later. Okay, then we have div-u divide unsigned. So it's going to treat the operands as unsigned, source 1 and source 2. It's going to divide, and it's going to round towards 0. So remember that when you're doing integer division in C, you can't get a floating point result. You can't get something with the decimal places and stuff like that. So it's basically going to say how many times does RS2 go into RS1 evenly, and basically then have the remainder stored elsewhere. So it's only sort of the division that goes an even number of times into the source 1. So concretely, if we had 5 and we divided it by 6, well, 6 goes into 5 0 times, and so the net result of that is 0. If, on the other hand, we had some very large unsigned number like f's ending in 7, and we divided that by 3, we would get this all 5's ending in 2. But we can perhaps have an intuition just by trying to multiply these back together that all of this 5's ending in 2 times 3, well, 3 times 2 is going to be 6, so this is probably going to be all f's ending in 6. So there's probably a 1 remainder here, and we'll see that when we look at the remainder operation next. Remu, remainder unsigned. Same thing, unsigned operands. The percentage or modulus operator in C is going to give you the remainder, and the remainder is kind of like if you did the source 1 divided by source 2, but keeping in mind that that's not going to be a floating point, so it's just the number of times that it goes in evenly, and then multiply that back times source 2. If there's any sort of remainder, this result will be less than this result, and so RS1 minus this result will give you whatever the leftover or remainder is after that division. So concretely, we had 5 divided by 6 before, but if we instead do 5 modulo 6, the result is going to be 5, because this RS1 divided by RS2 gave us a 0 before. That cancels out this entire term, so it's RS1, which is 5, minus 0, and the remainder is 5. Also, again, we had all f's ending in 7, and before the result of that division, so all f's ending in 7 divided by 3 gave us all 5's ending in 2, but basically I said all 5's ending in 2 times the 3 would probably give us all f's ending in 6, so this would be RS1 of all f's ending in 7 minus all f's ending in 6, and that gives us a remainder of 1. Okay, so now it's time for you to go look at the source code, look at the assembly, step through it in a debugger, and make sure you understand what's going on with these new instructions we learned. Multiply, keep the bottom x bits, divide as unsigned, and remainder as unsigned.